There are more than 2 trillion galaxies in the observable universe, each one containing hundreds of billions of stars, and around those stars orbit worlds we will never see, under skies we will never map. We have found black holes with masses billions of times that of our Sun. We have detected the echo of the Big Bang itself, still ringing faintly through the fabric of space. We have watched stars explode, witnessed galaxies collide, and measured the precise curvature of space-time near the edge of what light can reach. And yet, out of everything humanity has observed, calculated, and confirmed, there exists something so profoundly strange, so resistant to intuition that even the scientists who study it cannot fully reconcile what it means. It does not announce itself with violence. It does not glow or pulse or scream across the void. It simply exists, quiet and undeniable, forcing us to confront the uncomfortable truth that the universe operates by rules we barely understand, and in some cases, may never fully grasp. If you love deep space deep dives, you can subscribe. It helps more than you think. To understand what makes something truly strange in the context of the cosmos, we must first understand what scientists mean when they use that word. Strangeness, in this sense, is not mystery for its own sake. It is not the absence of explanation, but the presence of an explanation that defies expectation. A strange phenomenon is one that obeys the laws of physics, as far as we can tell, but does so in a way that feels impossible. It is the moment when the data comes back and the numbers are correct, the measurements are verified, the observations repeated, and yet the conclusion sits uneasily in the mind, refusing to settle into comfortable understanding. The universe is filled with violence and beauty, with explosions and slow dances of gravity across billions of years. But violence is not strange. Violence is expected. What unsettles scientists is not the supernova that destroys a star, but the object left behind that should not, by any reasonable standard, exist in the form it does. What unsettles them is not the speed of light, but the realization that time itself is negotiable, that two observers can disagree on the order of events and both be correct. Strangeness is the feeling that emerges when reality reveals itself to be far less intuitive than the mind assumes. Humans evolved to understand the world at a particular scale. We are built to perceive objects that are roughly our size, moving at speeds we can track with our eyes, over distances we can walk. Our brains developed to predict the arc of a thrown stone, the rustle of a predator in tall grass, the passage of a day into night. We are extraordinarily good at understanding the middle ground of existence, the realm where cause and effect are immediate and visible. But the universe does not limit itself to this scale. It extends in both directions into the unimaginably vast and the incomprehensibly small, and at both extremes, the rules that govern everyday experience begin to break down. A galaxy does not behave like a thrown stone. A photon does not behave like a rolling ball. And the farther we venture from the middle ground of human intuition, the stranger the universe becomes. Consider distance. The nearest star to Earth, beyond our own sun, is Proxima Centauri, just over 4 light years away. That means the light we see from that star tonight left its surface over 4 years ago. We are not seeing the star as it is, but as it was, and Proxima Centauri is, cosmically speaking, right next door. The Andromeda Galaxy, the nearest large galaxy to our own Milky Way, is 2.5 million light years distant. When we observe Andromeda, we are looking back in time to an era when early humans were just beginning to use stone tools. There are galaxies we can detect whose light has been traveling toward us for over 13 billion years, meaning we see them as they were when the universe itself was barely 500 million years old. At these distances, the concepts of now and then lose their meaning. There is no universal present tense. Every observation is an archaeological dig into the past, and the deeper we look into space, the further back in time we see. This is not a poetic metaphor. It is a literal consequence of the speed of light being finite. The universe does not permit us to see things as they are, only as they were. Time, too, behaves in ways that resist common sense. According to Einstein's theory of relativity, time is not a fixed, universal backdrop against which events occur. It is a dimension, interwoven with space, and it can stretch and compress depending on gravity and velocity. An astronaut traveling at a significant fraction of the speed of light will age more slowly than someone standing still on Earth. This is not an illusion or a trick of perception. It is a measurable physical effect. Atomic clocks flown on airplanes tick at different rates than identical clocks left on the ground, and the difference matches the predictions of relativity exactly. Near a black hole where gravity is immense, time slows dramatically. An observer falling toward the event horizon would, from their own perspective, cross it in finite time. But to someone watching from a safe distance, that observer would appear to freeze, asymptotically approaching the horizon, but never quite reaching it, their image redshifted into darkness. Both perspectives are correct. Time is not absolute. It is a local experience, shaped by the environment. This leads to one of the most disorienting realizations in modern physics: simultaneity is relative. Two events that appear to happen at the same time to one observer may occur in sequence to another observer, moving at a different velocity. There is no privileged reference frame, no objective "no" that all observers agree upon. If you were to point at a distant star and declare that something is happening there right now, the statement would be meaningless without specifying your reference frame. Another observer, moving relative to you, could legitimately claim that the event you pointed to has not yet happened or has already happened in the past. The universe does not provide a single, unified timeline. It provides a web of interdependent timelines, all equally valid, all slightly different. These are not philosophical abstractions. They are the foundations upon which our understanding of the cosmos is built, and they are strange, not because they are poorly understood, but because they are well understood and yet refuse to align with human intuition. We know they are true because we have tested them, measured them, built technologies that depend on them. GPS satellites, for instance, must account for relativistic time dilation, or their positioning data would drift out of accuracy within minutes. The satellites orbit at high speed and in weaker gravitational fields than clocks on Earth's surface, so their clocks tick faster. Engineers must correct for this. Relativity is not abstract theory. It is engineered into the devices we use every day. But even relativity, strange as it is, operates within a framework that can be mathematically described and experimentally verified. There are phenomena in the universe that push even further into territories where our current understanding begins to fray. Dark matter is one of these. In the 1930s, astronomer Fritz Zwicky observed the Coma Cluster, a large group of galaxies bound together by gravity, and noticed something wrong. The galaxies were moving too fast. According to the visible mass of the cluster, the galaxies should not have had enough gravitational pull to hold themselves together at the speeds they were moving. They should have flown apart long ago. Zwicky proposed that there must be some form of matter present that did not emit light, matter that could only be detected through its gravitational influence. He called it dark matter. For decades, the idea was treated with skepticism. It seemed too convenient, too much like invoking an invisible substance to fix an inconvenient problem. But then more evidence began to accumulate. In the 1970s, astronomer Vera Rubin studied the rotation curves of spiral galaxies and found the same problem. Stars at the outer edges of galaxies were moving just as fast as stars closer to the center, which made no sense. In a solar system, planets farther from the sun move more slowly, following Kepler's laws. The same should be true for galaxies. Stars at the edge should be moving slower than stars near the core, because there is less mass interior to them exerting gravitational pull. But they were not. They were moving at roughly the same speed, implying that there was far more mass in the galaxy than could be accounted for by visible stars, gas, and dust. The only explanation that fit the data was that galaxies are embedded in vast halos of dark matter, matter that does not interact with light at all but exerts gravitational force. Since then, evidence for dark matter has come from multiple independent sources. Gravitational lensing, the bending of light around massive objects, reveals the presence of unseen mass. The cosmic microwave background, the afterglow of the Big Bang, contains patterns that can only be explained if dark matter was present in the early universe, seeding the formation of galaxies. Computer simulations of cosmic structure formation only reproduce the observed large-scale structure of the universe when dark matter is included. Everything points to the same conclusion: the majority of matter in the universe does not emit, absorb, or reflect light. It is invisible. We know it is there because of what it does, not because we can see it. But what is it? That question remains unanswered. Dark matter is not simply matter that is dark, like a planet that does not emit light. It is something fundamentally different from ordinary matter, something that does not interact with electromagnetic radiation at all. It passes through normal matter almost without interaction, a ghost substance that shapes the universe but cannot be touched. Scientists have built detectors deep underground, shielded from cosmic rays, waiting for the rare occasion when a dark matter particle might collide with an atomic nucleus. So far, no confirmed detection has been made. Particle accelerators have searched for dark matter candidates, hypothetical particles that might fit the properties required. None have been found. Theories abound. Some propose new particles beyond the standard model of particle physics. Others suggest modifications to gravity itself, though these have struggled to match the full range of observations. Dark matter is not a mystery in the sense that it is poorly studied. It is a mystery in the sense that it is well studied, consistent across multiple lines of evidence, and yet completely unknown in its nature. And if dark matter is strange, dark energy is stranger still. In the late 1990s, two independent teams of astronomers were studying distant supernovae, stellar explosions that can be used as standard candles to measure cosmic distances. They were attempting to measure the rate at which the universe's expansion was slowing down. The expectation was straightforward. The universe has been expanding since the Big Bang, but gravity should be pulling everything back together, slowing the expansion over time. The question was how much it was slowing, which would tell us about the ultimate fate of the cosmos. Would the universe expand forever, or would it eventually collapse back in on itself? The data came back, and it did not match either scenario. The universe was not slowing down, it was speeding up. The expansion of the universe was accelerating. Distant galaxies were receding faster now than they were billions of years ago. This made no sense. Gravity is attractive. It pulls things together. There is no known force that should cause the universe to expand faster over time, and yet the supernova data was clear. The universe was accelerating. The discovery was so unexpected that both teams spent months checking and rechecking their work, searching for errors. There were none. The acceleration was real. The explanation, if it can be called that, is dark energy, a term that describes something we do not understand. Dark energy is not a substance in the traditional sense. It is a property of space itself, a kind of intrinsic energy that exists even in the absence of matter or radiation. The more space there is, the more dark energy there is, and as the universe expands, the amount of dark energy increases, driving the expansion faster. It is as if empty space has a pressure, a tendency to push outward, counteracting gravity on cosmic scales. The mathematics of general relativity allow for this. Einstein's equations include a term called the cosmological constant, which he originally introduced and then abandoned. That term, or something like it, now appears to describe dark energy, but we do not know why it exists, or why it has the value it does. Dark energy makes up roughly 68% of the total energy content of the universe. Dark matter makes up about 27%. Ordinary matter, the stuff of stars and planets and people, makes up less than 5%. Everything we see, everything we have ever touched, every atom in every molecule in every living thing, is a rounding error in the cosmic inventory. The universe is dominated by things we cannot see and do not understand. This is not a failure of science. It is a testament to how far science has come that we can even identify what we do not know. A century ago, the concept of dark matter did not exist. The expanding universe had not been discovered. Relativity was brand new. The idea that space itself could have energy would have seemed absurd. Today, we know these things are real because we can measure them. We cannot yet explain them fully, but we know they are there. The strangeness is not in the lack of data. It is in the data itself, which keeps pointing toward conclusions that stretch the limits of human comprehension. There are objects in the universe that challenge our understanding in different ways. Black holes are perhaps the most famous, and for good reason. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape. The boundary of a black hole is called the event horizon, and it is a point of no return. Once something crosses the event horizon, it is gone from the observable universe. It does not matter how fast it is moving or what it is made of. It cannot come back. The escape velocity at the event horizon exceeds the speed of light, and since nothing can move faster than light, escape is impossible. At the center of a black hole, According to general relativity lies a singularity, a point where density becomes infinite and the known laws of physics break down. This is not a comfortable conclusion. Infinity is not a number that appears in well-behaved physical theories. It is a sign that something is wrong, that the theory is being pushed beyond its limits. Most physicists believe that a singularity is not a real physical object, but rather an indication that general relativity is incomplete. At the extreme densities and energies of a black hole's core, quantum effects should become important, but we do not yet have a theory of quantum gravity to describe what happens there. The singularity is a placeholder for our ignorance. Black holes were predicted by general relativity, but for decades they were considered theoretical curiosities, mathematical solutions that might not exist in nature. Then, in the 1960s and 70s, astronomers began finding them. The first strong candidates were X-ray sources in binary star systems, places where a visible star appeared to be orbiting an invisible companion that was pulling matter off the visible star and heating it to millions of degrees, producing X-rays. The masses of these invisible companions were too large to be neutron stars or white dwarfs, the other known types of stellar remnants. They had to be black holes. Later, astronomers found evidence for supermassive black holes at the centers of galaxies, including our own Milky Way. These black holes have masses millions or billions of times that of the Sun, and they sit at the gravitational centers of their host galaxies, influencing the motion of stars and gas across vast distances. The black hole at the center of the Milky Way, known as Sagittarius A star, has a mass of about 4 million suns. We cannot see it directly, but we can see the stars orbiting around it, moving at thousands of kilometers per second, their orbits precisely traced over decades of observation. The orbits match the predictions for motion around a black hole of that mass. There is no other explanation that fits the data. In 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole's event horizon, or rather, the shadow it casts against the glowing gas around it. The target was the supermassive black hole at the center of the galaxy Messier 87, about 55 million light-years away. The image showed a dark circle surrounded by a bright ring of light, exactly as predicted by general relativity. The ring is the photon sphere, where light orbits the black hole before either falling in or escaping. The dark circle is the shadow of the event horizon. It was a triumph of observational astronomy and a confirmation that black holes are not just theoretical constructs. They are real, physical objects that can be observed and measured, but black holes are not the strangest thing in the universe, despite their reputation. They are strange, certainly, but they are well understood within the framework of general relativity. The equations are clear. The predictions match the observations. Black holes are extreme, but they are not anomalous. They fit comfortably within the structure of known physics. The same cannot be said for fast radio bursts. These are brief pulses of radio emission, lasting only a few milliseconds, coming from cosmological distances. They were first discovered in 2007, when astronomer Duncan Lorimer and his student David Narkevic were analyzing archival data from the Parkes Radio Telescope in Australia. They found a signal that had been recorded in 2001, a bright pulse of radio waves that lasted less than 5 milliseconds. The signal was strong, and it was clearly astrophysical in origin, not interference from human technology. But it was also strange. The pulse showed dispersion, a spreading out of different frequencies that occurs when radio waves travel through plasma. The amount of dispersion indicated that the signal had traveled through a vast amount of material, far more than could be accounted for by the gas in our own galaxy. The burst had come from far beyond the Milky Way. Since then, hundreds of fast radio bursts have been detected. Most appear to be one-time events, single pulses that occur without warning and are never seen again. A few, however, repeat. One of the first repeating sources, known as FRB 121102, has been observed to emit dozens of bursts over several years. The repeating bursts allowed astronomers to pinpoint the source to a small dwarf galaxy about 3 billion light-years away. This was a major step forward because it provided a host galaxy and a specific location, which could be studied in detail. But the question remains, what causes them? The energy released in a fast radio burst is immense. In just a few milliseconds, these bursts emit as much energy as the sun produces in several days. That energy is concentrated in radio wavelengths, which is unusual. Most high-energy astrophysical events, like supernovae or gamma-ray bursts, release energy across a broad spectrum, from radio to gamma rays. Fast radio bursts are overwhelmingly radio bright, which suggests a different mechanism. The leading theories involve magnetars, a type of neutron star with extremely powerful magnetic fields. Magnetars are known to produce intense bursts of X-rays and gamma rays, and it is plausible that under certain conditions, they could also produce radio bursts. But this is still speculative. No one has yet observed a magnetar producing a fast radio burst in real time, in a way that conclusively links the two phenomena. The strangeness of fast radio bursts lies not only in their power, but in their unpredictability. They do not fit neatly into existing categories. They are not supernovae, which take weeks to brighten and fade. They are not pulsars, which emit regular, periodic pulses. They are not gamma-ray bursts, which occur at higher energies. They are something else, something that was not anticipated by theory. And that is what makes them strange. They were discovered by accident in archival data, and their existence forces astronomers to consider mechanisms and environments that were not part of the standard picture of the universe. Then there are cosmic voids, regions of space that contain very few galaxies, almost empty expanses between the dense filaments of the cosmic web. The large-scale structure of the universe resembles a foam, with galaxies clustered along thin filaments and sheets surrounding vast voids. These voids are not merely empty space. They are regions where the density of matter is significantly below the average density of the universe. They can be hundreds of millions of light years across, and they contain only a handful of galaxies, if any. In 2024, astronomers identified what they called the Boötes supervoid, a region of space roughly 330 million light years in diameter, containing about 60% fewer galaxies than would be expected in a typical region of that size. The void is so large that light takes hundreds of millions of years to cross it, and its existence raises questions about the early universe. How did such a large underdense region form? The standard model of cosmology predicts the formation of voids as a natural consequence of gravitational collapse. In the early universe, matter was distributed almost uniformly, with tiny fluctuations in density. Over time, denser regions attracted more matter, growing into galaxies and clusters, while underdense regions lost matter, becoming voids. This process is well understood on smaller scales, but the Boötes supervoid and others like it are larger than standard models comfortably predict. They push the boundaries of what the current cosmological framework can explain. There is also the cold spot, an unusually cold region in the cosmic microwave background, the faint glow of radiation left over from the Big Bang. The cosmic microwave background is remarkably uniform, with temperature variations of only a few parts per 100,000. But the cold spot is colder than the surrounding area by about 70 microkelvins, and it is larger than expected from random fluctuations. Some astronomers have suggested that it could be the imprint of a supervoid along the line of sight, a region where the lower density of matter causes photons to lose energy as they pass through. Others have proposed more exotic explanations, including the possibility that it is a signature of a collision between our universe and another, a remnant of a multiverse interaction. This latter idea is highly speculative and not widely accepted, but the fact that it is even discussed reflects how difficult the cold spot is to explain within conventional cosmology. The strangeness of the cold spot is not that it exists, but that it should not be as pronounced as it is. Random fluctuations in the cosmic microwave background are expected, and they have been mapped in exquisite detail by satellites like the Wilkinson Microwave Anisotropy Probe and the Planck spacecraft. The statistical properties of these fluctuations match the predictions of the standard cosmological model almost perfectly, but the cold spot is an outlier, a feature that appears to be more extreme than the model predicts. It could be a statistical fluke, a rare but allowable fluctuation, or it could be a sign that something about the early universe was different from what we assume. The universe is also strange in its large-scale homogeneity. When viewed on the largest scales, hundreds of millions of light years and more, the distribution of galaxies is remarkably uniform. This is surprising because For that uniformity to exist, different regions of space must have been in causal contact at some point, meaning they must have been able to exchange energy and information, smoothing out any initial irregularities. But according to the standard Big Bang model, without modification, the universe expanded so rapidly that distant regions of space were never in causal contact. They were always beyond each other's light horizons. So why do they have the same temperature and density? The answer, according to the theory of cosmic inflation, is that the universe underwent a brief period of exponential expansion in the first fraction of a second after the Big Bang. During this inflationary period, a tiny patch of space, small enough to be causally connected, expanded to a size much larger than the observable universe today. This smoothed out any initial irregularities, explaining the large-scale uniformity we observe. Inflation also explains the tiny fluctuations in the cosmic microwave background, which are the seeds of all structure in the universe. Quantum fluctuations in the inflating space were stretched to macroscopic scales, and these fluctuations became the density variations that eventually collapsed to form galaxies. Inflation is a successful theory in the sense that it makes predictions that match observations. But it is also strange in its own right. It requires a new form of energy, a scalar field that drove the exponential expansion, and we do not know what that field was or whether it still exists. Inflation predicts that the universe should be flat, meaning that parallel lines will never meet or diverge, and observations confirm that the universe is indeed flat to within a small margin of error. But inflation also predicts that our observable universe is just a tiny part of a much larger whole, possibly an infinite multiverse where different regions have different physical laws. This is a profound and unsettling conclusion, one that takes the Copernican principle to its extreme. Not only is Earth not the center of the universe, not only is the Sun an ordinary star in an ordinary galaxy, but our entire observable universe might be just one bubble among an infinite number of bubbles, each with its own properties. This touches on a deeper question. Why does the universe have the properties it does? Why is the strength of gravity the value it is? Why do electrons have the mass they have? Why does the cosmological constant have the value we observe? These are not questions that physics, as currently formulated, can answer. Physics describes how the universe behaves, not why it has the specific parameters it does. Some physicists have argued that the parameters are fine, tuned for the existence of complex structures like stars, planets, and life. Change the strength of gravity by a small amount, and stars might not form, or they might burn too quickly to allow life to develop. Change the mass of the electron, and atoms might not exist in the form we know. This fine tuning is sometimes presented as evidence for design, or for the anthropic principle, which states that we observe the properties we do because, if they were different, we would not be here to observe them. The multiverse offers a different perspective. If there are an infinite number of universes, each with different parameters, then it is not surprising that we find ourselves in one where the parameters allow for our existence. This is not a satisfying answer in the traditional sense, because it does not explain why our specific set of parameters exists, only why we are in a universe that has them. It shifts the question rather than answering it, and it raises a troubling possibility. If the multiverse is real, then many of the parameters we observe are accidents of our particular bubble, and there is no deeper reason for them. They are simply the result of random quantum fluctuations during inflation. This moves the discussion into territory that makes many scientists uncomfortable. The multiverse is, by definition, unobservable. If other universes are beyond our light horizon, then we can never see them, measure them, or test their properties. They are, in principle, forever out of reach. This does not mean the multiverse is not real, but it does mean that it may be beyond the reach of empirical science. Some physicists argue that this does not matter, that the multiverse is a prediction of a theory that makes testable predictions in other areas, and therefore it should be taken seriously. Others argue that, without observability, the multiverse is not science but metaphysics. The tension between what we can observe and what we can theorize is a recurring theme in cosmology. We can only see a finite region of space, the portion from which light has had time to reach us since the Big Bang. Beyond that boundary lies more universe, perhaps infinitely more, but it is invisible to us. We can infer properties of the universe beyond the observable horizon from the properties of the observable universe, but we cannot be certain. The universe may be infinite, or it may be finite but unbounded, like the surface of a sphere. We do not know. We may never know. There are also objects that are strange not because of what they are, but because of what they do to space-time. Gravitational waves, ripples in the fabric of space-time itself, were predicted by Einstein in 1916, but they were not directly detected until 2015, nearly a century later. The Laser Interferometer Gravitational Wave Observatory, LIGO, detected the collision of two black holes, each about 30 times the mass of the Sun, at a distance of over 1 billion light years. The collision released more energy in a fraction of a second than all the stars in the observable universe combined. That energy was radiated away as gravitational waves, distortions in space-time that traveled outward at the speed of light. When the waves reached Earth, they stretched and compressed space by a distance smaller than the width of a proton, a change so tiny that it required the most sensitive instruments ever built to detect. The detection of gravitational waves opened a new window on the universe. For the first time, astronomers could observe events not through electromagnetic radiation, light and radio waves and X-rays, but through the medium of space-time itself. Since that first detection, dozens more have been recorded, including collisions of black holes, collisions of neutron stars, and possibly even more exotic events. Neutron star collisions are particularly interesting because they produce both gravitational waves and electromagnetic radiation, allowing astronomers to observe them in multiple ways simultaneously. The collision of two neutron stars in 2017, observed by LIGO and dozens of telescopes around the world, confirmed that these events produce heavy elements like gold and platinum, elements that cannot be forged in normal stellar fusion. The universe's supply of heavy elements, including the gold in jewelry and the platinum in catalytic converters, was created in neutron star collisions and scattered into space, later to be incorporated into new stars and planets. Gravitational waves also offer a way to test general relativity in extreme conditions. The black hole collisions detected by LIGO involve objects moving at significant fractions of the speed of light in regions where space-time is severely curved. The waves themselves carry information about the masses and spins of the colliding objects, and they match the predictions of general relativity with extraordinary precision. If relativity were wrong or incomplete, in these extreme environments, the gravitational wave signals would deviate from the predictions. So far, they have not. But gravitational waves also reveal the strangeness of space-time. When a gravitational wave passes through you, it does not push you or pull you in the traditional sense. It changes the distance between points in space. If you were floating in space with another person a meter away, a passing gravitational wave would alternately stretch and compress the distance between you, making it slightly longer and then slightly shorter. You would not feel this. The change is far too small and it affects everything, including the atoms in your body. But it is real. Space itself is flexible, dynamic, responsive to mass and energy. This is not an abstract concept. It is a measurable, observable fact. The universe also contains objects that are strange because they are the remnants of processes we do not fully understand. Magnetars, mentioned earlier in connection with fast radio bursts, are neutron stars with magnetic fields trillions of times stronger than any magnetic field we can create on Earth. Neutron stars themselves are already extreme. They are the collapsed cores of massive stars compressed to such density that a sugar, cube-sized amount of neutron star material would weigh as much as a mountain. Protons and electrons have been crushed together to form neutrons, and the entire star, with a mass greater than the Sun, is packed into a sphere only about 20 kilometers across. The surface gravity is so intense that a fall from a height of 1 centimeter would result in an impact with the energy of a large bomb. Magnetars take this to another level. Their magnetic fields are so strong that they distort the vacuum around them, affecting the way light propagates. The fields can trigger starquakes, sudden rearrangements of the neutron star's crust, which release enormous bursts of X-rays and gamma rays. These bursts are so energetic that they have been detected from distances of tens of thousands of light years, and they can temporarily ionize Earth's upper atmosphere, even from across the galaxy. The mechanism that creates such powerful magnetic fields is not entirely understood. It likely involves the rapid rotation and intense magnetic dynamo processes in the newly formed neutron star, but the details remain unclear. There are also objects called quasars, which are among the most luminous objects in the universe. A quasar is powered by a supermassive black hole at the center of a galaxy, accreting matter at a prodigious rate. As matter falls toward the black hole, it heats up to millions of degrees and emits radiation across the electromagnetic spectrum. A single quasar can outshine an entire galaxy, despite the fact that the energy is coming from a region smaller than our solar system. The light from quasars has been traveling for billions of years before reaching us, so when we observe them, we are seeing the universe as it was in its youth, when galaxies were still forming and black holes were growing rapidly. But quasars are not just bright, they are also strange in their abundance. The number of quasars peaks at a redshift corresponding to a time when the universe was about 3 billion years old, and then it declines. Today, quasars are much rarer. This tells us something about the history of galaxy formation and black hole growth, but the exact details are still being worked out. It appears that the era of rapid black hole growth coincided with the era of intense star formation, and as galaxies settled into more stable configurations, the fuel supply for both stars and black holes diminished. But why the peak occurred when it did, and why it was so pronounced, is not fully explained. The universe is also strange in its overall fate. The discovery that the expansion of the universe is accelerating means that the future is very different from what was once imagined. If the acceleration continues, as current observations suggest it will, then the universe will expand forever, and the expansion will speed up over time. Distant galaxies will recede from us faster and faster, until eventually they cross a boundary where their light can no longer reach us. The observable universe will shrink, not because space is contracting, but because the accelerating expansion carries distant objects beyond the point where their light can catch up to us. In trillions of years, the only galaxies we will be able to see are those in our local group, the small cluster of galaxies bound together by gravity. Everything else will have vanished beyond the horizon. Stars will continue to form for a while longer, but the supply of gas will eventually run out. Star formation will cease, and the existing stars will age and die. Low-mass stars, red dwarfs, will continue to burn for trillions of years, but eventually even they will exhaust their fuel. The universe will enter an era dominated by stellar remnants, white dwarfs, neutron stars, and black holes. These remnants will slowly cool, radiating away their heat into the expanding void. Galaxies will dissolve as stars are ejected through gravitational interactions, and black holes will slowly evaporate through Hawking radiation, a quantum process by which black holes lose mass over immense timescales. A solar mass black hole will take about 10 to the 67 years to evaporate. A supermassive black hole will take even longer. In the end, if we wait long enough, the universe will consist of nothing but low-energy photons and perhaps some stable elementary particles spread out over an ever-expanding space at a temperature indistinguishable from absolute zero. This ultimate fate is far stranger than the alternative once imagined, the Big Crunch, in which the universe would eventually stop expanding and collapse back in on itself, possibly triggering a new Big Bang. The Big Crunch had a kind of symmetry to it, a sense of closure. The accelerating expansion offers no such comfort. It suggests that the universe will not end in a dramatic event, but in a slow fade, a gradual dissipation of energy into an ever larger volume of space until nothing of interest remains. But the strangest aspect of all this may not be any single object or phenomenon, but the overarching realization that the universe is comprehensible at all. The laws of physics, as far as we can tell, are the same everywhere in the universe and at all times. A hydrogen atom on Earth behaves the same way as a hydrogen atom in a galaxy 10 billion light years away. Gravity follows the same inverse, square law whether it is acting on a falling apple or on a galaxy cluster. This universality is not obvious. There is no a priori reason why the laws of physics should be the same everywhere, or why they should be expressible in the language of mathematics, or why they should be discoverable by creatures like us, evolved on a small planet orbiting an ordinary star, and yet they are. We can write down equations that describe the behavior of black holes, the expansion of the universe, the quantum fluctuations in the early cosmos, and those equations match observations to extraordinary precision. This is deeply strange. The universe did not have to be this way. It could have been chaotic, lawless, utterly resistant to understanding. But it is not. It is structured, orderly, governed by principles that can be tested and verified. This points to something even stranger, the role of mathematics in physics. Mathematics is a human invention, a set of abstract symbols and rules developed to describe patterns and relationships. And yet, when physicists write down mathematical equations to describe nature, those equations work. They make predictions that turn out to be correct. They reveal connections between seemingly unrelated phenomena. Maxwell's equations, for example, unified electricity and magnetism into a single electromagnetic force, and they predicted the existence of electromagnetic waves, including light, before anyone had observed such waves directly. Dirac's equation, developed to describe the behavior of electrons in a way consistent with both quantum mechanics and relativity, predicted the existence of antimatter before it was discovered. Time and again, mathematics developed for abstract reasons has turned out to describe the physical world with uncanny accuracy. Einstein famously remarked that the most incomprehensible thing about the universe is that it is comprehensible. This was not a throwaway comment. It was an expression of genuine wonder at the fact that the universe submits to rational analysis. Why should it? Why should the patterns we observe locally hold true across billions of light years and billions of years of time? Why should the universe be governed by laws at all, rather than operating by caprice or chaos? These are not scientific questions in the traditional sense, because science takes the existence of laws as a starting point, a foundational assumption. But they are questions that arise naturally from the practice of science, and they are among the strangest aspects of existence. There are also phenomena that are strange because they seem to violate causality, at least on the surface. Quantum entanglement is one of these. When two particles are entangled, a measurement on one particle instantaneously affects the state of the other, no matter how far apart they are. This was famously troubling to Einstein, who called it spooky action at a distance, and believed it indicated that quantum mechanics was incomplete. He thought there must be hidden variables, some deeper layer of reality that would restore locality and determinism. But experiments, starting with those of Alain Aspect in the 1980s and continuing to the present day, have confirmed that entanglement is real, and that there are no hidden variables of the type Einstein imagined. The correlations between entangled particles are stronger than any classical theory can produce, and they occur instantaneously, without any signal passing between the particles. This does not allow for faster than light communication, which would violate relativity. The measurement results on one particle are random, and the correlation with the other particle only becomes apparent when the two sets of results are compared, which requires communication through ordinary means. But the fact remains that the universe allows for non-local correlations, connections between distant events that do not rely on anything traveling through the space in between. This is deeply counterintuitive. Our everyday experience is entirely local. Objects interact by touching, or by exchanging particles or waves that travel from one place to another. The idea that two particles can be connected in such a way that a measurement on one instantly determines the state of the other, without any mediating mechanism, defies all intuition, and yet it is true. Quantum entanglement is not a theoretical curiosity. It is a well-established experimental fact, and it is being used in the development of quantum computers and quantum cryptography. The strangeness of quantum mechanics goes deeper than entanglement. At the quantum level, particles do not have definite properties until they are measured. An electron does not have a definite position or momentum. It exists in a superposition of states, a spread of possibilities, until an observation forces it to choose one. This is not ignorance on our part. It is not that the electron has a definite position and we just do not know what it is. The electron genuinely does not have a definite position until it is measured. This has been tested in countless experiments, most famously the double-slit experiment, where a single electron passing through two slits produces an interference pattern, as if it went through both slits at once. But when a detector is placed to determine which slit the electron goes through, the interference pattern disappears, and the electron behaves as if it went through one slit or the other, but not both. The implications of this are profound and disturbing. It suggests that reality, at the quantum level, is not made up of definite objects with definite properties, but of probabilities and potentialities that only become actualized when observed. This raises the question of what constitutes an observation. Does it require a conscious observer, or is any interaction sufficient? The latter is the mainstream view among physicists. A measurement is any interaction that causes the quantum system to become entangled with a larger environment, a process called decoherence. Consciousness is not required, but the question of what, if anything, is real before a measurement is made remains a matter of interpretation. Some interpretations, like the Copenhagen interpretation, hold that it is meaningless to talk about the properties of a system before measurement. Others, like the many worlds interpretation, hold that all possible outcomes of a measurement actually occur, each in a different branch of reality. The universe, in this view, is constantly splitting into countless branches, one for each possible outcome of every quantum event. We only perceive one branch, but the others are equally real. These interpretations are not idle speculation. They are serious attempts to make sense of the mathematical structure of quantum mechanics and the results of experiments. But they lead to wildly different pictures of reality. In one interpretation, the universe is fundamentally probabilistic and indeterminate until measurements collapse the wave function. In another, the universe is deterministic and everything that can happen does happen in some branch of the multiverse. Both interpretations are consistent with the same experimental data. This is unsettling. It means that science, for all its power, cannot always tell us what is really happening, only what we will observe under given conditions. The strangeness of quantum mechanics is compounded by the fact that it seems to conflict with general relativity. Quantum mechanics describes the behavior of particles on small scales, while general relativity describes the behavior of spacetime on large scales, and the two theories are incompatible. In quantum mechanics, time is absolute, a background against which events occur. In relativity, time is part of spacetime, malleable and observer-dependent. Quantum mechanics is probabilistic. General relativity is deterministic. Attempts to merge the two into a theory of quantum gravity have been ongoing for nearly a century, with no definitive success. String theory is one candidate, proposing that particles are not point-like but are tiny vibrating strings. Loop quantum gravity is another, proposing that spacetime itself is quantized, made up of discrete chunks. Neither theory has been experimentally confirmed, and both face significant mathematical and conceptual challenges. The need for a theory of quantum gravity is not purely academic. There are places in the universe where both quantum effects and strong gravity are important, places where general relativity and quantum mechanics must both apply. The singularity at the center of a black hole is one. The Big Bang itself is another. At the moment of the Big Bang, the entire observable universe was compressed into a region smaller than an atom, where quantum effects would have dominated. To understand what happened in that first instant, we need a theory that combines quantum mechanics and gravity. Without it, we can only trace the universe's history back to a fraction of a second after the Big Bang, the Planck time, about 10 to the minus 43 seconds. Before that, our current theories break down. We do not know what happened. We do not even know if the question makes sense, because time itself may not have existed in the form we understand. This ignorance is not a failure. It is an acknowledgement of the limits of current knowledge, and it is a spur to further research. But it is also humbling. For all our progress, for all the galaxies we have mapped and the particles we have discovered, there are fundamental questions we cannot answer. What happened at the very beginning? What is the nature of time? What is the quantum structure of spacetime? Why does the universe exist at all? These questions sit at the boundary of physics and philosophy, and they may remain there for a long time. There are also anomalies, observations that do not fit comfortably into the current framework. The Hubble tension is one of these. The Hubble constant is a measure of how fast the universe is expanding, and it can be determined in two ways. One way is to measure the distance and velocity of nearby galaxies, using objects like Cepheid variable stars and supernovae as distance markers. This gives a value for the Hubble constant of about 73 kilometers per second per megaparsec. The other way is to use the cosmic microwave background, extrapolating forward from the early universe to the present day using the standard cosmological model. This gives a value of about 67 kilometers per second per megaparsec. The two values disagree by more than the estimated uncertainties, and the disagreement has persisted as measurements have become more precise. This is called a tension rather than a contradiction because it is not yet clear whether it represents a real problem or a subtle error in one or both measurements. But if the tension is real, it suggests that something is missing from the standard cosmological model. Perhaps dark energy behaves differently than we assume. Perhaps there is an unknown component to the universe's energy budget. Perhaps general relativity is not quite correct on cosmological scales. Or perhaps the early universe was more complex than the simple models we use. The tension is not dramatic. It does not overturn the Big Bang model or demand a radical rethinking of cosmology. But it is nagging, persistent, and it refuses to go away as data improves. This is the kind of anomaly that, historically, has led to new discoveries. The anomalies in Mercury's orbit led to general relativity. The anomalies in galaxy rotation curves led to dark matter. The Hubble tension may yet lead somewhere new. Another potential anomaly involves the distribution of satellite galaxies around large galaxies like the Milky Way and Andromeda. In simulations of galaxy formation that include dark matter, large galaxies are predicted to have many small satellite galaxies orbiting them, distributed more or less randomly in three-dimensional space. But observations suggest that the satellite galaxies of the Milky Way and Andromeda tend to lie in thin planes, rotating in the same direction. This is unexpected. It could be a statistical fluke, or it could indicate that something about the formation process is not captured in the simulations. It could even suggest that the nature of dark matter is different from what we assume. Cold dark matter, the standard assumption, consists of slow, moving particles that clump together under gravity. If dark matter is warm, moving faster, it might behave differently on small scales. Or if dark matter interacts with itself through some unknown force that could alter the distribution of satellite galaxies. These are speculative ideas, and none is widely accepted, but they illustrate how even small anomalies can open up new lines of inquiry. The universe also contains structures that seem almost impossible. The Hercules Corona Borealis Great Wall is a massive structure, a filament of galaxies stretching across more than 10 billion light years. It is so large that light takes 10 billion years to travel from one end to the other. This is a significant fraction of the age of the universe. The existence of such a large structure challenges the cosmological principle, the idea that the universe is homogeneous and isotropic on large scales. Structures this large take a long time to form, and it is not entirely clear how they could have formed in the time available since the Big Bang. Simulations of structure formation can produce large filaments, but the Hercules Corona Borealis Great Wall is at the extreme end of what models predict. It is not a contradiction, but it is uncomfortable, a reminder that the universe can produce things that strain the limits of our expectations. There are also smaller scale mysteries. The solar system itself contains oddities. The orbit of the dwarf planet Sedna, for example, is highly elongated, taking it far beyond the Kuiper Belt, the region of icy bodies beyond Neptune. At its farthest point, Sedna is nearly 1,000 astronomical units from the Sun, where 1 astronomical unit is the distance from the Earth to the Sun. This is so far that the Sun would appear as just a bright star, barely distinguishable from other stars in the sky. The orbit is also tilted relative to the plane of the solar system. Something must have perturbed Sedna into this orbit, but it is not clear what. Neptune is too far away, and its gravity too weak to account for it. Some astronomers have proposed that a distant, undiscovered planet, sometimes called Planet 9, might exist in the outer solar system, massive enough to have influenced Sedna and other distant objects. Searches for this planet have so far come up empty, but the possibility remains. Closer to home, there are puzzles about Earth itself. The Moon, for example, is unusually large relative to Earth. Most moons in the solar system are much smaller than the planets they orbit, but Earth's moon is about 1/4 the diameter of Earth. The leading explanation for this is the giant impact hypothesis, which proposes that, early in Earth's history, another planet-sized object, sometimes called Theia, collided with Earth. The impact vaporized much of both objects, and the debris coalesced to form the Moon. This hypothesis explains many features of the Moon, including its composition, which is similar to Earth's mantle but lacks a large iron core. But the details are still being worked out. How large was Theia? How fast was it moving? At what angle did it strike? These questions matter because they determine the properties of the resulting Moon, and getting the details right requires careful simulation and comparison with observations. The origin of life on Earth is another mystery, though it is a biological rather than astrophysical one. Life appeared on Earth relatively quickly after the planet cooled enough to have liquid water, possibly within a few 100 million years. This suggests that the emergence of life, at least in simple form, may not be exceedingly rare. But we do not know how it happened. We do not know how non-living chemistry transitioned into self-replicating, evolving systems. We do not know whether life started in shallow tidal pools, in deep-sea hydrothermal vents, or even in space, delivered to Earth by comets or meteorites. We do not know whether RNA came first, or whether some simpler replicating molecule preceded it. These are active areas of research, but definitive answers remain elusive. And this matters for astrobiology, the study of life beyond Earth. If we do not understand how life started here, it is hard to estimate how common it might be elsewhere. The search for extraterrestrial life is itself a strange endeavor. We have found thousands of exoplanets, planets orbiting other stars, and many of them are in the habitable zone, the region where liquid water could exist on the surface. But we have not yet found any definitive sign of life. This could mean that life is rare. It could mean that life is common but intelligent. Technological life is rare. It could mean that we are not looking in the right way, or that the signs of life are too subtle for our current instruments to detect. Or it could mean that we are alone, that Earth is the only planet in the observable universe that has produced life. This last possibility is profoundly strange, not because it is implausible, but because it makes humanity cosmically unique, a status that seems at odds with everything else we have learned. The universe is vast, ancient, and filled with planets. It seems unlikely that we are the only ones. But absence of evidence is not evidence of absence, and until we find life elsewhere, the question remains open. The Fermi paradox encapsulates this strangeness. If the universe is so large and so old, and if planets are common, then where is everyone? Why have we not seen any signs of extraterrestrial civilizations? There are many proposed solutions. Perhaps intelligent life is rare. Perhaps it is common but self-destructs before it can spread across the galaxy. Perhaps advanced civilizations are quiet, uninterested in communication, or using methods we have not thought to look for. Perhaps they are already here, observing us, and we do not recognize them. Perhaps interstellar travel is harder than we imagine, or perhaps the timescales involved are so vast that civilizations rise and fall without ever overlapping. None of these solutions is entirely satisfying, and the paradox remains unresolved. The speed of light imposes a fundamental limit on communication and travel. The nearest star system, Alpha Centauri, is over 4 light-years away. A radio signal sent there would take over 4 years to arrive, and the reply would take another 4 years to return. This makes real-time conversation impossible. For more distant stars, the delays become absurd. A signal to a star 1,000 light-years away would take 1,000 years to arrive. Any civilization on a planet around that star would be responding to a message sent by our ancestors in the Middle Ages, and we would receive their reply 1,000 years after we sent ours. This is not a limitation of technology. It is a limitation of the universe itself. Information cannot travel faster than light, and the vast distances between stars mean that the universe imposes a kind of isolation on any civilization that arises. Interstellar travel faces the same problem, compounded by the difficulty of accelerating massive objects to high speeds. A spacecraft traveling at a significant fraction of the speed of light would require enormous amounts of energy, and it would face hazards like interstellar dust and cosmic rays. Even at 10% the speed of light, a fast pace by any reasonable standard, it would take 40 years to reach Alpha Centauri. Human lifespans are not long enough for such journeys unless we develop suspended animation, or unless we accept that the travelers will spend their entire lives aboard the spacecraft, with their descendants arriving at the destination. These are not insurmountable problems, but they are severe, and they may explain why, If other civilizations exist, they have not spread across the galaxy. Or perhaps they have, and we simply have not noticed. The galaxy is large, about 100,000 light years across, containing several 100 billion stars. Even if a civilization could travel between stars, it would take millions of years to colonize the entire galaxy. We have been broadcasting radio signals for only about a century, a tiny blip in cosmic time. If another civilization is out there, and if they are aware of us, they might not yet have had time to respond. Or they might have visited long ago, before humans existed, and left no trace we would recognize. Or they might be so different from us, so alien in their thought processes and motivations, that we would not recognize their activities as the work of intelligence. The universe is also strange in its silence. The cosmic microwave background is a faint hiss of radio noise, the leftover radiation from the Big Bang, but it is remarkably quiet. There are no loud, obvious signals from distant civilizations, no beacons, no broadcasts. We have searched using radio telescopes, listening for narrow band signals or pulses that would indicate artificial origin. We have searched the sky for optical flashes, brief pulses of laser light that might be interstellar communication attempts. We have looked for megastructures, vast engineering projects that might alter the light from stars. We have found nothing. This does not prove that we are alone, but it is consistent with being alone, or at least being the only technological civilization within listening distance. And listening distance, in this context, is limited. Our searches have covered only a small fraction of the sky, and they have only been sensitive to very specific types of signals. A civilization using different communication methods, or one that is deliberately quiet, would go unnoticed. There is also the question of what we would do if we found a signal. The protocols for this are not well established. There have been discussions, and there are informal agreements among scientists involved in the search for extraterrestrial intelligence. But there is no binding international treaty, no clear plan for how humanity would respond. Some argue that we should not respond at all, that broadcasting our presence could be dangerous. Others argue that any civilization capable of reaching us would already know we are here, and that remaining silent gains nothing. The debate is largely theoretical, because we have not found anything to respond to. But it is a strange debate nonetheless, a discussion of how to interact with something that may not exist. The strangeness of the universe extends to its beginning and its end, to the boundaries of time itself. The Big Bang is not an explosion in space, but an expansion of space. Before the Big Bang, there was no space, no time, no matter, no energy. Or at least, that is the standard interpretation. The concept of before the Big Bang may not make sense because time itself began with the Big Bang. This is philosophically troubling. We are used to thinking of cause and effect, of events having prior causes. But if time begins at the Big Bang, then there is no before in which a cause could exist. Some physicists have proposed that the Big Bang was not the true beginning, that the universe goes through cycles of expansion and contraction, or that our universe budded off from a pre-existing multiverse. These ideas are speculative, and they push the question back rather than answering it. If the universe is cyclic, what started the cycle? If our universe came from a multiverse, what created the multiverse? The end of the universe, as mentioned earlier, appears to be a slow fade into darkness, driven by the accelerating expansion. But there are other possibilities. If dark energy is not constant, if it changes over time, then the future could be different. If dark energy grows stronger, the acceleration could become so extreme that it tears apart galaxies, then stars, then planets, then atoms, in a scenario called the Big Rip. If dark energy becomes negative, causing space to contract, the universe could collapse in a big crunch. If quantum fluctuations eventually destabilize the vacuum, the universe could undergo a phase transition, a sudden change in the properties of space itself, in an event called vacuum decay. This would propagate outward at the speed of light, destroying everything in its path, rewriting the laws of physics as it goes. There would be no warning. One moment everything is fine, the next moment a bubble of new vacuum is expanding toward you, and when it arrives, you and everything around you cease to exist in any recognizable form. These scenarios are not predictions, they are possibilities, consistent with what we know but not required by it. The universe could end in any of these ways, or in some other way we have not imagined. or it could continue indefinitely, expanding and cooling until nothing remains but the faintest possible echoes of the structures that once existed. In any case, the end is unimaginably far in the future, trillions upon trillions of years away, long after the sun has burned out, long after the last stars have died. It is not something that poses any immediate concern, but it is strange to think about, to contemplate the ultimate fate of everything that exists. The strangeness of the universe is not confined to exotic objects and extreme events. It is also present in the everyday, in the fact that stars shine at all. The sun produces energy through nuclear fusion, combining hydrogen atoms to form helium and releasing energy in the process. This energy travels outward, taking thousands of years to work its way from the core to the surface, and then it streams into space as light and heat. That light takes 8 minutes to reach Earth, where it warms the surface, drives the weather, powers photosynthesis, and makes life possible. This is a process we understand in detail, but it is also miraculous in its own way. The sun is a stable, self-regulating fusion reactor, maintaining a balance between gravity pulling inward and pressure pushing outward, and it has been doing this for nearly 5 billion years. It will continue for another 5 billion until the hydrogen in the core runs out and the sun begins to die. But fusion should not work as well as it does. The protons in the sun's core are positively charged, and they repel each other. To overcome this repulsion and get close enough to fuse, they need to have very high energy, which means very high temperature. The core of the sun is hot, about 15 million degrees Celsius, but it is not hot enough for protons to overcome the electrostatic repulsion through thermal energy alone. Classical physics says that fusion should not occur at the temperature and density of the sun's core, and yet it does. The reason is quantum mechanics. Protons can tunnel through the energy barrier, a quantum effect that allows particles to appear on the other side of a barrier they do not have enough energy to cross. This tunneling is rare, but there are so many protons in the sun, colliding so frequently, that enough fusion events occur to power the sun. Without quantum tunneling, stars would not shine, and the universe would be a cold, dark place. This is strange. The existence of stars, and therefore of planets, and therefore of life, depends on a quantum effect that has no analog in everyday experience. It depends on particles behaving in ways that seem impossible, passing through barriers they should not be able to cross. And this is not unique to stars. Quantum effects are everywhere, underlying the structure of matter, the behavior of atoms, the chemical reactions that make life possible. The reason atoms are stable, the reason electrons do not spiral into the nucleus is quantum mechanics. The reason molecules form, the reason DNA can store information, the reason your brain can think, all depend on quantum effects. The strangeness of quantum mechanics is not a curiosity, it is foundational. There is also the strangeness of consciousness itself, the fact that the universe contains observers, beings capable of understanding it. Consciousness is not well understood. We do not know how subjective experience arises from the physical processes of the brain. We do not know why there is something it is like to be you, why you have a first-person perspective, why the world appears to you as it does. This is called the hard problem of consciousness, and it is hard because it is not clear how to even approach it scientifically. We can study the brain, map its neurons, trace the flow of signals, identify which regions are active during different tasks. But none of this explains why there is an experience associated with those processes, why there is a subjective quality to perception and thought. Some philosophers argue that consciousness is an illusion, a trick the brain plays on itself, and that there is no hard problem at all. Others argue that consciousness is fundamental, that it cannot be reduced to physical processes, and that any complete theory of the universe must include it as a basic feature. Still others argue that consciousness is an emergent property, something that arises from the complex interactions of simpler components, and that we will understand it once we understand those interactions well enough. None of these positions is proven, and the debate continues. But if consciousness is real, if it is not an illusion, then its existence is strange. It means that the universe is not merely a collection of particles obeying laws, but also a place where those particles can organize themselves into structures that experience, that feel, that wonder. It means that the universe contains not only matter and energy, but but also meaning, perspective, the sense of being someone. This is not something physics addresses. Physics describes how things behave, not what it is like to be those things. And yet consciousness exists. You exist. You are reading these words, processing their meaning, constructing a mental model of the universe as it is described. This is remarkable, and it is strange that beings like us, products of evolution on a single planet, can understand the universe at all. Evolution shaped our brains to survive and reproduce in a specific environment, the African savanna, where the challenges were immediate and practical: finding food, avoiding predators, cooperating with others. There was no evolutionary pressure to understand black holes or quantum mechanics or the expansion of the universe. And yet we can. We can take the cognitive tools we evolved for survival and extend them through mathematics and instrumentation and collaboration to comprehend phenomena far beyond our direct experience. This is not guaranteed. It could have been that the universe was comprehensible only on the scales and conditions relevant to survival, and that anything beyond that was forever beyond our reach. But it is not. We can understand the very large and the very small, the very fast and the very slow, the long ago and the far away. This suggests that the universe, strange as it is not arbitrary. It operates by principles that are discoverable, and those principles are powerful enough to explain a vast range of phenomena. But there are limits. There are questions we may never be able to answer, not because they are intrinsically unanswerable, but because they lie beyond the reach of observation. The interior of a black hole is one. Once something crosses the event horizon, no information about it can escape. We cannot send a probe into a black hole and receive data back. We cannot observe what happens at the singularity. We can make predictions based on theory, but we cannot test them. The singularity is, in a very real sense, removed from the observable universe. Similarly, the state of the universe before the Big Bang, if such a concept even makes sense, is beyond our reach. We cannot observe it, because all information from that time, if it existed, was erased by the Big Bang itself. We can speculate, we can construct theories, but we cannot verify them through observation. This is frustrating, but it is also a reminder that science is not about achieving perfect, complete knowledge. It is about asking questions, testing hypotheses, and refining our understanding based on evidence. There will always be questions at the boundary, questions that we do not yet know how to answer, and some of those questions may remain unanswerable. But that does not diminish the value of what we do know. We know an extraordinary amount about the universe, far more than any previous generation. We know how stars form and die. We know how galaxies evolve. We know the age of the universe to within a few million years, out of nearly 14 billion. We know the composition of the cosmos, the proportions of ordinary matter, dark matter, and dark energy. We know the history of the universe from a fraction of a second after the Big Bang to the present day. This knowledge is not complete, and it is not perfect, but it is real, and it is profound. The strangeness of the universe, then, is not a single thing. It is not one object or one phenomenon. It is a quality, a property that emerges from the universe's refusal to conform to human intuition. It is the realization that distance is time, that time is relative, that matter is mostly empty space, that empty space is not empty, that particles can be in two places at once, that the universe is expanding and accelerating, that most of the universe is made of things we cannot see, that the laws of physics are the same everywhere but lead to outcomes that seem impossible. The strangeness is not a bug, it is a feature. The universe is strange because it is vast, because it operates on scales far beyond the human, because it follows rules that were not designed for our convenience. And perhaps the strangest thing of all is that we are here to notice. We are made of atoms forged in stars, scattered into space by supernovae, gathered into a new generation of stars and planets, and eventually organized into living beings capable of looking back at the universe and asking questions. We are the universe examining itself, a small part of the cosmos that has become conscious and curious. This is not a common occurrence. As far as we know, it may be rare, possibly even unique, but it has happened at least once, here, now, in you and in every other person who has ever looked up at the night sky and wondered. The universe does not owe us understanding. It does not present itself in ways that are easy to grasp or comfortable to accept. It simply is vast and strange and indifferent, governed by laws that care nothing for human preferences. And yet, despite this, or perhaps because of it, we keep looking, keep questioning, keep building better instruments and better theories, pushing the boundaries of what is known. We do this not because it is easy, not because it promises practical benefit, though sometimes it does, but because we are curious. We want to know, we want to understand, and in that wanting, in that relentless questioning, there is something profoundly human and profoundly strange. The universe may never fully reveal itself. It may always hold mysteries just beyond our reach, questions that sit at the edge of the knowable, and perhaps that is how it should be. The strangeness is not a problem to be solved. It is an invitation to keep exploring, to keep wondering, to keep reaching toward the horizon that forever recedes before us.